Let's take a few examples and see where we go with it. All right, number 2. Which form of electromagnetic radiation has the longest wavelength? Now, there are a couple of approaches you can use for this. You can just memorize them. Or you can develop an intuition that says longer wavelength means lower energy. And we all, well, most of us in the sciences, have a feel for which ones have the highest energy. Like gamma rays are the highest, X-rays next, right? Then ultraviolet, then visible, and then infrared, and radio waves, and then I skipped microwaves, and then radio waves. So the radio wave should be the lowest energy and the longest wavelength. The longest wavelength should be the smallest, I was trying to pick the right word, the smallest frequency. If I say short or long frequency, that's throw you off. But in this case, we're looking for the longest wavelength is radio waves. Let's see, number 3. Let me move some of these out of my way. Either that or I can look at the boards. Which of the following frequencies correspond to light with the longest wavelength? Well, the shortest wavelength will be the highest frequency. So the smallest frequency will be the longest wavelength. And that's simply because of this relationship. Right? They're inversely proportional. So if this gets longer, that gets smaller. If this gets shorter, that gets bigger. So the longest wavelength should have the smallest frequency value. And the smallest frequency value I see there is, just look at the powers of 10, right? And as long as they're different, you can settle on that one. If you run across 2 or more that are the same power, then you have to look at the coefficient. But this one says that B, that 4.12 times 10 to the 5th reciprocal seconds or hertz will answer that question. That one has the longest wavelength if that is the value for frequency. Okay. Number 6. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. That's the wavelength. Okay. When mercury emits a photon of light at this wavelength, the frequency of this light is. All right, so there's some blue smoke in that problem. All right, some of that information you don't need. Question is, convert the wavelength into frequency. Right. So we're back to here. So frequency is going to be speed of light divided by wavelength, but we have to have SI units. Those are not SI units, right? So when I get something like that, the simplest way I think is to say, what does nano mean? Nano means 10 to the minus 9 meters. Okay. And I just punch that into my calculator because it'll accept non-scientific notation just fine. You can put 254, then exponent minus 9, and that would go in here. What goes up here? 2.9979 times 10 to the 8th meters per second. And that would be divided by 254 times 10 to the minus 9th meters. Okay, so denominator, numerator, those cancel. And there's your reciprocal seconds, which is the same as hertz. And if we do our calculations correctly, it should be 1.18 times 10 to the 15. 0.18 times 10 to the 15 hertz or reciprocal seconds. Let's see if that makes sense. If we take this one down here to that one, then this would be -7. So that's a little over 1. Okay, that fits here. How about this one? Well, if you divide by a negative power, it's the same as adding a positive power. Right? So that becomes +7 plus a +8 is a 15. Okay. Looks reasonable. Number 8. Green light can have a wavelength of 543 nanometers. Why does it say can have? Because green is relative to our physiology. At that wavelength, we'll see green. But maybe a wavelength of 540, you may see green too. So we're given the exact value here. So that's quantitative versus qualitative description. The energy of the photon of this light is. Okay. So what formula are we going to need here? Planck's constant times frequency. Well, that's not frequency. So if we solve frequency from our equation, we get C over lambda. So now we can say Planck's constant times C over lambda. So Planck's constant is what? I don't remember. 6.626 something, right? Yeah. 10 to the minus 34. So Planck's constant is 6.626 times 10 to the minus 34. Correct units. Those kilogram meter squared per second. Oh, joule second. That's a better one. Because we're looking for energy. So we would use joule seconds here. Then we have our speed of light, 9979 times 10 to the 8th meters per second, divided by the wavelength in meters. So if I do like I did before, I'd have 10 to the minus 9 meters. Okay. So check our units. Meters cancel. Seconds is reciprocal. This is in the denominator, that's in the numerator. So they cancel. We're left with joules, so that's good. Now, if we do the calculation correctly, we should end up with 3.66 times 10 to the minus 19 joules. Okay. Too much math this early in the morning? Oh, wait a minute, it's afternoon already. We'll be awake by now. Unless you pulled an all-nighter. I guess that can happen, especially in the medical profession. Okay, how about number 11? Go. How many of the following are correct? So that means maybe none of them are correct, or maybe all of them are correct. So let's see. First one, the importance of the equation E equals mc squared is that energy has mass. Yeah. It's equating mass to energy. You don't think of yourself normally as, I'm a ball of energy. If you converted all of me into energy, you'd have probably a hydrogen bomb. I mean, that because of this factor. You square a number that's 10 to the 8th, right, times the mass in kilograms, and you're going to get a huge value for joules. So they, I'm trying to remember what they call it. When you take the mass of, say, uranium-235 and the mass of its products, when it splits, it produces a couple of different elements, plus some elementary particles that go flying off, neutrons and electrons and so forth. Well, they don't call them electrons. They call them beta particles. But if you add all the mass up afterwards and subtract it from the mass before, then you get that mass value. Stick it in that equation, that tells you how much energy was produced by that one split. Mass deficiency, I think they call it. Okay, 2. Electromagnetic radiation can be thought of as a stream of particles called photons. Oh, yeah. That's fair. Electromagnetic radiation exhibits wave properties. That's 2. Yep. And energy can only occur in discrete units called quanta. Yep, they're all correct. Okay, let's see. All right, 12, 13, 14, and 15 refer to this table. 12, 13, 14, and 15. All right. Which one of these, A through E, clearly supports the conclusion for question, start with 12? Electrons have wave properties. How do we know they have wave properties? What physical demonstration of wave properties do we see in that table? The emission spectrum of hydrogen. That doesn't say anything about wave properties. Photoelectric effect? No, that's not purely wave, right? Einstein sort of combined wave and particles there. Scattering of alpha particles by metal foil. Oh, that's, well, it calls them particles, right? So they can't be waves. In that description, diffraction. Diffraction. What is diffraction? You remember? You can draw it 2 different ways. You can draw it as a slit, and you got a wave coming in here. When it hits this barrier, then this point serves, this slit serves as a point source for a new wave. So it starts there and it grows like that. If there were just particles, they go straight through and you'd see nothing on either side. So that's diffraction. All right, so D is the correct one here. How about 13? Electromagnetic radiation has wave characteristics. That's the same thing. It's another way of saying 12. Right? Oh, no, wait a minute. Electrons have wave properties. We can see diffraction. This is number 12 again. Diffraction of electrons. And we built that into a very powerful instrument called an electron microscope. Right? There's a diffraction limit to using light in a microscope. And anything smaller, you can't see the difference between 2 points. That's the diffraction limit. If you use something with a shorter wavelength than light, then you can differentiate particles or places that are closer together. And that's what we do with electrons. So electromagnetic radiation has wave properties also because it exhibits diffraction. Cathode rays, we didn't talk about that one. A cathode ray is a stream of electrons. That's all it is. And I don't know if any of you still have television sets with the tubes in them. I had one until a couple of years ago and it finally crapped out, the last one. So now I'm all flat panel. But they used cathode rays in there. They had a ray gun back here, and they had electric and magnetic fields that were oscillated to control where the electrons go, and it would scan across the screen like that. And this phosphor tube in the front is where the picture would be produced. And they were extremely heavy, especially if you got a big one like 25 or 36-inch screen. Okay, let's see, 14. Electrons in atoms have quantized energies. Right? Electrons have quantized energies. What's the evidence for that? The emission spectrum of hydrogen is a good example, right? You only get certain lines because the electrons can only move between levels. Nothing in between. It's not continuous. It's discrete. The electron movement is quantized, and that is expressed as individual lines in a spectrum. So A would be for number 14. And 15, spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. We haven't talked about de Broglie wavelength, have we? We just mentioned his name. But de Broglie, I'm pretty sure he was French. Worked, he was a brilliant mathematician, and he drew the comparison between the wavelengths of anything that has mass. Right? Einstein said you can turn mass into energy with his equation, but de Broglie says, all right, if I have a particle that has this mass, what is its actual wavelength? And he devised formulas that would do that. The de Broglie, when you talk about wavelength, you're talking about diffraction, because that's the only thing in that list that refers to waves exclusively is diffraction. Now, if we just said refraction, same thing. Refraction is a process built upon the wave nature of anything. Okay. So that last one is also D. D-dad. Let me see if I've got de Broglie's formula in here. We might want to use it. Well, if we need it, I'll look it up. Someplace else besides useful information. 16. All right. The 4 lines observed in the visible emission spectrum of hydrogen tell us that what? Well, we sort of introduced that topic in the last question. Those 4 lines indicate that electrons can have only certain energies in a hydrogen atom. Nothing in between. All right, so D is the best answer for that one. 17? Yeah, I'm going to 17. For which of the following transitions does the light emitted have the longest wavelength? Okay, here's where that first question that we looked at here, where you equated energy to wavelength. Long wavelength means low energy. And low energy is a short jump for an electron. So where's the shortest jump? Remember, when you have a nucleus and you got one principal quantum number 1 there, 2 is like here, then 3 gets closer, and 4 gets even closer than that. Right? So the jump between 4 and 3 would be a longer wavelength, lower energy, than a jump between 4 and 2 or 3 and 2. 4 to 3 or 3 to 2 or 2 to 1. 4 to 3 would be a longer wavelength, lower energy. So that's in our choices, that's A. Now we can actually calculate those values. I mean, we have a formula for that. But this is reasoning time, not calculation time. We'll get there eventually. When hydrogen electron makes a transition from n equals 3 to n equals 1, which of the following statements is true? Okay. If it goes from N3 to N1, that's our electron, what happens? Well, it's coming from a high energy state to a low energy state. So it gives up energy as a light wave. Okay, now where does that fit here? Energy is emitted, yes. Roman numeral 1 is true. It can't be emitted and absorbed, so 2 is out. 3, the electron loses energy. Yep, as it goes from higher to lower, it loses energy. So those 2 are true for sure. And 4 is the opposite of 3, so it can't be that one. Electron cannot make this transition. That's a filler. Couldn't think of a fifth one, so we just throw that one in there for fun. Right? So it's Roman numeral 2 and Roman numeral 3, which is 1 and 3, excuse me, is B. Okay, 21. Which of the following is incorrect? Notice I put those in italics to draw your attention. Attention to detail. The emission spectrum of hydrogen contains a continuum of colors. A, that's false. Contains a line spectrum, not a continuum. Diffraction produces both constructive and destructive interference. Yeah. Well, it can. If you have light waves coming through one slit, then no. But if you have light waves coming through 2 slits, you definitely get constructive and destructive. So we have to qualify that statement if we're going to say that it's true. We're looking for the false one. All right, so we found it already. If we want to look at the rest of them. C, all matter displays both particle and wave-like characteristics. Yep, it sure does. And Niels Bohr developed a quantum model for the hydrogen atom. Yep. He modeled it on the planetary system. The lowest possible energy state of a molecule or atom is called its ground state. Yes. I don't know if I mentioned that earlier, but that's what we mean. Ground state. Now, the ground state is the lowest possible energy under certain conditions. So on Earth, at room temperature and pressure, we're going to have a ground state where all the electrons are packed as close as they can get to the nucleus. Right? Temperature is not high enough to add any energy to them. If you go to a hypothetical planet where the temperature is like 1,000 degrees on the surface, then its ground state is going to have electrons are going to be further out because you're adding energy to them. All right, 22. Like maybe Venus, right, where you can melt lead on the surface. That might be a different ground state. I'm not saying it is, but it could be. Which of the following statements best describes the Heisenberg? All right, I always mess this one up. I have to look at it. Do I have the formula in here? Have I done? No, I don't see it. Okay, I better not receive it. Let's just define it in words. What does the Heisenberg uncertainty principle say? Well, it says that you can't, at the elementary particle or atomic level, you can't know both where an atom is or where a particle is and how fast it's moving. It's energy. You can't know the energy and its position at the same time. Now it's expressed in terms of position and momentum, mass times velocity. And I'm tempted. Should be greater than or equal to h over, is it 4 pi? Something like that. I hope that's right. I'm gonna look it up. Heisenberg. I know we covered it in class. See if you can find it first. Must be way back over. HC over. No, that's not it. That's not it. That's the wrong one. There it is. H over 4 pi. I got it. Got it right. Shazam. Well, I'll let that parentheses. Okay, so which one of these fits that definition? C looks like the best one. It's impossible to accurately know both the exact location and the momentum of the particle. That's what this is. This is a deviation in position. So if this is very large, that means you can't know where it is. If it's very small, then we can accurately determine its position. If this is very large, since the mass doesn't change, then we can't know its velocity, and velocity for any particle means energy. We opt for knowing the energy of electrons around the atoms. That's more useful information than position. So we sort of statistically say, all right, the electrons have this energy, and if they do, they're going to be somewhere in this region. And we can say things like, here's a node. Uh-oh. It's still sharing. Okay. It didn't drop out here, so I guess it was just that TV that messed up. I hope that's all it was. Okay. I've done enough talking. Let's go to 25. Actually, there are several of them in a row that are based upon the same concepts. 25. Now we're going to talk about atomic structure. So maybe if it were a new topic for me and I were taking a test as a student, I might memorize some things and then put them in the margins, right? Before I even look at the questions. I just write them down, right? So N is the principal quantum number. L is the, let's see, principal quantum number. Momentum quantum number. Magnetic quantum number and spin quantum number. And this one can be 1, 2, 3. This one can be 0, 1, 2, up to n minus 1. This one can be minus L to 0 to plus L, whole number increments. And this one can be plus 1/2 or minus 1/2. Okay, so that's what I put in the margins, and then I wouldn't have to dredge those out of my brain. I could work on the question instead. How many F orbitals have the value n equals 3? Well, we have to go to letters now. This is L0 is S, 1 is P, 1, and that one's D, and then 3 is F. So how many have the value n equals 3? How many F orbitals have the value n equals 3? Okay, if n equals 3, what can we have here? 0, 1, 2, right? No F's. Okay. So the answer to that one is 0. Can't have any F's at that level. Okay, trick question. How about 26? How many f orbitals have n equals 6? Okay, if you go to 6, and by the way, this is a shell, this is a subshell, and this is the orbital. So when they say orbitals, they're talking about m sub l's. Okay. All right, so the conditions here are n equals 6. And how many f orbitals will there be? Well, if n equals 6, then L can equal, well, you can have an L of f, right? So you can have a 3, you can have a 0, 1, 2, 3, 4, and 5, and there's your f. So then m sub l's will be what? -3, -2, -1, 0, +1, +2, +3. 1, 2, 3, 4, 5, 6, 7. Okay. So you have 7 f orbitals. 7 orbitals in the f shell, subshell. Okay. So that's B. Let's see, the first one was A. 27. If n equals 2, how many orbitals are possible? Now we're talking about total orbitals at n equals 2. So L can be what? L can be 0, 1, that's it. Yeah. So then we go m sub L for 0, right? For 0 is just 1, right? M sub L would be 0. This one can have -1, 0, +1. So you can have 4 orbitals for n equals 2. Okay. 28, we're still talking about, sort of. 28. A given set of p orbitals consists of set of p orbitals. Okay, I guess that's correct terminology. Just kind of twist your head around a little bit. So p is going to be 1. If L is 1, then m sub L can be -1, 0, +1. So it can only have 3. That's, see? Yeah. 3 orbitals. Which 29, which of the following is an incorrect designation for an atomic orbital? Okay. Let's check them out. So 1s, 3d, 1p, 4f, and 6s. All right. For something like this, which of the following is incorrect? I'll find the ones that are correct. Right. N equals 1, you can always have an S. It's 0. Right. So that one's correct. You can always have an S for any of the others. It doesn't matter what their principal quantum number is. You can always have S's. 3D, right? 3 would be here. And no, 3 would be here. And D would be SPD, 2. Yeah. Because 3 can have 0, 1, and 2. Right. So that one's good. 1P. No. You can only have 0 or S for a 1. So there's our bad one. And then 4 can have F. We did one of those earlier. So the bad one is 1P. It doesn't exist. All right. Let's make some room here. Not erasing as good as I thought it would. Okay. 31. Time. A point in a wave function where the amplitude is 0 defines what? This is just definition. A wave function that has an amplitude of 0 is a node by definition. What does it tell us? If the wave function is 0, that means probability that we find an electron there is 0. That's what that means. That's a node. How many electrons in an atom can have the quantum numbers N3 and L2? So if it's N3, can it have a 2? Yeah, 0, 1, and 2. Yep, so that's true. So the question is, how many electrons with these two numbers? And now we have to go to M sub L, which is -2, -1, 0, +1, +2 orbitals. And each one of these can have 2 electrons, right? 1, 2, 3, 4, 5, 10 electrons. All right. Now, where do we find elements that are filling that shell? Right. SPD. We find them right in here. Transitions. These transitions, not the inner transitions. These transitions. The inner transitions are filling F orbitals. Okay, that was 31 and 32. Is this boring? No? Okay. I mean, I don't want to go over something that you already have in the vice grip. Let's see. How many electrons can be described by the quantum numbers N3, L3, ML1? Well, by the time you get down to ML1, oh, wait a minute. That's a trick question. Let's see if it's even possible. Yeah, this is a trick question. N equals 3, and L can be 0, 1, or 2. Okay, that one's good. That's 2. We're given 2. How about, oh, excuse me. No, L3. Excuse me. I'm looking at the wrong one. L3, no. Can't have any electrons there. Doesn't matter what else is below it. That's it. It's all over with. Yeah. Bank's got all your money, time to leave the casino. All right. 34. What is the L quantum number for a 4s orbital? 4s. That's possible, yeah. So N equals that. That means L is that, correct? Yeah, L quantum number, that's equal to 0. S's are 0, L number. Okay, 37. Good. Which of the following combinations of quantum numbers NL, M sub L, M sub S do not represent permissible solutions of the Schrodinger equation? For the electron in the hydrogen atom, in other words, which combination of quantum numbers is not allowed? Right. Go down to E. E says all are allowed. So we've got, I'm going to put them in there like this. N, L, M sub L, and M sub S. And list them down like that. So we got 9866, 9866, and then L is 82 minus 55, 82 minus 55, and M sub L is -4, 2, -1, -5. 2, -4 and -5. We'll say that. Nope, -2, sorry. Bad short-term memory. And the rest are plus 1/2. Okay, which one of these would not be allowed? Well, would 8 be allowed here? Yeah. 0 through 8 would be allowed. Okay, so that's okay. How about this one? Well, if we go from 8 here would be -8 would go through -4. Yeah. So this whole thing, and of course, that's always allowed. That one's okay. How about this one? 8, 2. Yeah. 2 would be okay. We'd start with 0, 1, 2. That one's okay. Can we get a 2 out of this one? Yeah. -2, -1, 0, 1, and 2. So that one's okay. How about this one? Can you get a -L? No. Start with 0 and go up to n-1. So that one's bad. So it can't be this one because all are not allowed. And this one would be 0 through 5 would be good here. -5 here. Let's see, 5. Yeah. It'd be -5 to +5. That's okay. So this is the one that's bad. See. All right, number 40. Test your memory. Questions. Who was the first chemist to recognize patterns in chemical properties of the elements? The temptation is to say Mendeleev, but it wasn't. The first one was the one, remember we talked about triads. Triads were Dobereiner. I mean, he didn't take them any further than that. He just noticed that 3 elements had similar properties, like, chlorine, bromine, iodine, or sodium, potassium, rubidium, things like that. Just the triads. That's all he was concerned with. He must have had some other things in the hopper, and he didn't have time to mess with it, or he didn't care. That's possible. 41. Okay, Mendeleev is given the most credit for a concept of periodic table of the elements because, remember why? Remember, at this time, they didn't know about protons and electrons, neutrons. All they knew was element properties, their reactivity with other elements, their weights, their relative weights. They still were having trouble getting absolute weights, but the relative weights, yeah, they knew those. And Mendeleev ordered everything by properties and weights, right? And when he came to a place where the next one was the next highest weight, but if he put it in that group, it wouldn't have the same properties, similar properties to the group. So instead of putting it there, shifted it over one and says, fits there pretty good. So what's the problem? We're missing an element. Nobody's discovered it yet. So he didn't leave it there. He said, there's going to be an element there one of these days, and it's going to have these properties, and it's going to have this weight. That's why he gets most of the credit. So that would be B. He emphasized usefulness in predicting existence properties of unknown elements. Yay. And he was a school teacher, by the way. Probably some student asked him a question he couldn't answer, so he went out and created the periodic table. I don't know, it's just speculating. 44. The complete electron configuration of 10. So you got to know the symbol for 10. Got to find it on the periodic table. As neutral 10 has 50 protons and 50 electrons. So then you either go to periodic table, you know how it's structured, or you go to that diagonal chart and you start adding your orbitals in order of increasing energy. Right? But if you do that, let's do it by the periodic table. So here's 10. What have we gone through so far? And we have to do the whole thing. It asks for the complete. We got to do the whole thing. Well, it's gone through 1s, it's gone through 2s and 2p, 3s and 3p. So we know we got those in there. 1s, 2s, 2p, 3s, 3p. We know we got those in order. And then we got 4s. And then what comes after 4s? Transition metals, we drop down 1 for the Ds. So the next is 3D. Then we go across there and we go back to the 4Ps with this period right here. Then we go down to the 5s and 4D. And by the time we get to 10, we're into the 5P again. So it's 5P2. We know that's going to be at the very end. And the rest of them are going to be full because we've passed through all the elements in the process. So we just have to put the right number here. 2, 2, 6, 2, 6, 2, 10, 6, 2, 10. That should add up to 50. So let's see, that's 10. And that's another 10, that's 20, 30, 40, 6, 10, 50. Okay. That's the way I like to do it. If you understand how the periodic table is structured, that's nothing. All right. 46. Oh, while we're here, what's the abbreviated version? You back up until you find, you go back until you circle back around. Krypton would be the core. Okay. So that leaves what? That leaves 5s, 4d, and 5p. So these would go down right here. And that would be your abbreviated version. Okay. Finish erasing that. What did I say? 46. Okay. The statement that, okay, I like to look at the answers sometimes. Aufbau, Hans rule, Heisenberg, Pauli exclusion model. Okay. So we're going to identify what that statement references. The lowest energy configuration for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals. Okay, I didn't use that word before, did I? Degenerate orbitals. So when you have p orbitals, you can have -1, 0, +1, right? If you have d orbitals, you can have -2, -1, 0, +1, and +2. These are considered degenerate. I mean, they're not perverts. They're the same energy. That's what degenerate means. Don't ask me why they picked that name. So what principle are we describing here? Hund's rule. Hund's rule says, as you add electrons in these degenerate orbitals, they have to be unpaired first. And if you have more than 3 in this case, then you can start pairing them up. And the primary reason for that is when you pair up electrons, you got 2 negative charges there pushing away from each other. Lower energy means you keep them separated, okay, until you have to put them together. Okay, 47. Okay, an element has the electron configuration of krypton, 36. Doesn't show it there, but I like to put that in there. Oh, wait a minute, we just drew that. 5S 4D10 5P2. That's 10. 50. Okay. Well, it wants the question is, where does it fit? It's a non-metal transition element, metal, lanthanide, actinide. Well, it's not an actinide or lanthanide. It's not down here. It's up there in the representative elements. But which side of that squiggly line is it on? It's on the left-hand side. All right, so it's a metal. Is it close enough to be a transition metal? I mean, not transition, but a metalloid. Metalloid's not your choice, so that's a non-issue. But which ones would be considered metalloids then? If we had one that was, say, here and here, maybe here and here, here and there, those might be metalloids. 10's not close enough. It doesn't share a complete border with anybody else. So it's still a metal. Transition metal. No, it's a metal, not a transition element. It's a metal. Okay. 48. An element with electron configuration xenon. Xenon 54. And then 6S 4F 5D7. 6S 4F 5G7. Would belong to which class in the periodic table? All right. If you're filling d orbitals, it's going to be a transition metal. 5D. We go to 6 to get to the 5Ds. So 5D would be, actually, that would be 7. 2, 3, 4, 5, 6. Probably iridium. Is that 77? 16, 23. Yeah, 77. That's iridium. Iridium. Where have I seen that? Oh. You remember, I don't remember the geologists' names. It was the father and son team, and they noticed a pattern. There was this place in layered rocks that was a different color. And they took samples from all over the world and analyzed them and found an elevated amount of iridium in them. And the one thing about iridium is most rocks on the Earth, in the Earth's crust, don't have a lot of iridium in them. But you will find a significant amount of iridium in asteroids. So then they started dating the layers and found they all came from the same layer, same age, roughly. And it was about 65 million years ago. So they said, that coincides with the disappearance of the dinosaurs. So they speculated that, based on evidence, that maybe the dinosaurs were blown away by this big rock. Now, we found where it probably landed, right? Just off the Yucatan Peninsula in the Gulf of America. But it blew all that iridium into the air, and then it settled down into this layer. Okay. So we answered the question already, didn't we? Yeah. All right. All alkaline earths have the following number of valence electrons. A valence electron is what? Well, all the valence electrons in an element's configuration have the same principal quantum number. So if you're looking at alkaline metals, where are they? Oh, no, alkaline earths, excuse me. Alkaline earths, the second column. And those, you're putting 2 electrons in the s orbital for each one of those. So beryllium would be 2s, magnesium 3, calcium 4, strontium 5s, so forth. And those would have 2 valence electrons because they would have 2 electrons in that uppermost orbit. Right. So that's why D is there. The 2 electrons. That's why when we went to naming compounds, say in ionic compounds, the alkali metals always have a +2 charge. So that makes them type 1 naming convention. Okay, that's why. Because they lose those 2 electrons. You lost 2 negatives, now you have an excess of 2 positives. That's why it has a 2 positive charge. I don't know, it might have been easier if I'd have told you up front what that was. Should we do this chapter first and then do naming compounds? I don't know. Let's see. Allison. Okay. She must have dropped off and come back on. Okay. 50. More time. About 15 minutes. Titanium has how many electrons in the d orbital? Simplest way to do titanium is just find it on the periodic table. Right? There it is. Second one over from scandium. Scandium has D1, titanium has D2. It has 2 electrons in the d orbital. Yeah. Okay. All right. Let's see. 52. Iron has blank electrons that are unpaired in its d orbitals. All right. This is going to take a little bit more work. So if we look at iron, which d orbital is being filled? Well, it's 3D, right? 3D. And then we were at 4s at first. 3D then is 1, 2, 3, 4, 5, 6 for iron. Okay. We want to know how many unpaired electrons. So with d orbitals, with p you got 3 orbitals, with d's you got 5, because 2 times 5 is 10, and you've got 10 elements across there. So we have 1, 2, 3, 4, 5. Now, is this going to be an anomaly? No. We can't fill the d's and we can't do half d's to make it more stable. Right? We're stuck with 6. So it's 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4 unpaired electrons in d orbitals. All right. Okay, we're going to be looking at this chart up here for 53 and 54. So let's put, yeah, we can see the whole thing there. 53 and 54. Okay. 53, which represents the ground state for nitrogen? And we're saying ground state on planet Earth. 7. So we got 1s2, 2s2, 2p, 3. Right? Well, it's drawn in the electrons with their spins, right? And 1s is left out. So we're only interested in these here, 2, 3, 3, like that. So that's your ground state. That would be A. Okay. How about N minus? Well, N minus is still going to have 7 protons, but now it has 8 electrons. Where are they going to go? Well, if we're still just looking at S and P's, then we do this. Then we add the other one. You can pair it up. All right. So that's going to be E was the best one for that. According to Hund's rule. 55. In which group do all the elements have the same number of valence electrons? Really, all we have to do, A, B, C, D, and E. E says none of them, right? And we already see this none. So what we're looking for is, are they in the same columns? Right? Phosphorus, sulfur, and chlorine. Well, phosphorus and sulfur are in two different columns, so it can't be that one. Right? B is silver, cadmium, and argon. You got a noble gas in there, and the rest of them are not noble. Okay. Sodium, calcium, barium. Sodium is an alkaline metal. Calcium and barium are alkaline earths. So that one doesn't work either. And phosphorus, arsenic, and selenium. Phosphorus and arsenic are good, but then we stick selenium in there. It's in a different group, right? Selenium is a chalcogen, and phosphorus and arsenic are pnictogens. Right? So that tells us that their valence electron numbers are not the same for all members of the groups. So none of them. Okay, 58. Of the following elements, which has occupied d orbitals in its ground state, neutral atom? All right. A, B, C, D, and E. So we got barium, calcium, silicon, phosphorus, chlorine. All right. The condition is occupied d orbitals. So if we look at barium, barium has already cycled through two sets of d orbitals already, right? So it's got electrons in its d orbitals. They're just not valence electrons. Okay. How about calcium? Calcium hadn't got to the D's yet. 4s, 3D's coming, but it's not there yet. So this one doesn't have any. Is that what we were looking for? Which has, oh, no, we eliminate everything except the one, of course, we found it. So if you're pressed for time, just mark that down and move on. But for those reasons, silicon is still in the third period. It's never made it to the D's. Phosphorus also, and chlorine. They've not made it to the d orbitals yet. Only barium. Let's see, 62. Which of the following atoms has 3 electrons and p orbitals in its valence shell? 3 electrons in its valence. Okay. So all right. So I don't get tripped up by my own question. Let's put these down. Barium, gallium, vanadium, bismuth, and okay, we're looking for has 3 electrons in its p orbital. 3 electrons in p. Valence shell. Okay. So barium has a 6s. That's its valence shell, right? Anything that's the highest number it has, right? Anything less than that is 4s and 5s. All right, so it only has 2 electrons in its valence shell. Gallium, it has 1 electron in the p. Well, that's 2 electrons in the s. Right, so it doesn't qualify on either count. Gallium does have a p orbital, right? But it's only got 1 electron. Right? So it has, let's see, 4p, 4p1. Vanadium, has a 3D3. How did it get there? Well, there's a 3S and a 3P. 3P, actually for vanadium, that's 3D, 3P. So it has 3 in its 3Ds, and it has 5 in its 3P. It has 3P, excuse me, has 6 in its 3P. And then we intersperse before. So it actually has 6 in its p orbital, excuse me, 6 in its p orbital, 1 in its p orbital. That one has none. How about bismuth? Where's bismuth? Bismuth's over here. 1, 2, 3p, 6p, 6p3. There's your answer. Did I lose anybody? Okay. All right. Let's see. 66. Running out of time, folks. Which of the following is the highest energy orbital for a silicon atom? All right, where's silicon? Got it here. 3p2. Silicon has a 3p2, it has a 3s2. Right? And everything is below that. Highest energy orbital for a silicon atom. Well, the S's are slightly different in energies. Right? Remember, the S has something like, well, let's see, it has one of these, then it has one of these, then it has one of these. And the P, the 3p, only has 2 humps. So the 2 humps are in here sort of like this, and excuse me, and like this. So the S is lower energy because it penetrates deeper. All right. So which of the following is the highest energy orbital? It will be the 3p. Be higher energy than the S. Now the principal quantum number gives you the energy level in terms of region, right? But the subshells break that down even further. 67. Which of the following processes represents the ionization energy of bromine? All right, you just have to know the definition. Ionization energy, you take the neutral atom, and we're assuming that it's a neutral atom. This is the first ionization energy. And it looks like all of our answers have non-charged bromine. And it has to be a gas. Then you add energy to it, and you kick off 1 electron, and you're left with a negative ion, gaseous. Right. Well, the electron, they put the electron on the other side. Oops, excuse me. Balance my charges. This is a positive ion. This is a negative. So that would be C. Would fit best. 68. Okay, order the elements SClF in terms of increasing ionization energy. Sulfur, chlorine, and fluorine. Right, we know that ionization energy trends this like that from lower left to upper right. So we look at their relative positions. Sulfur, chlorine's to the right, fluorine's above. So it would be this order, right? This would have a greater ionization energy. Is it from least to greatest? Increasing, yes. So sulfur, chlorine, fluorine. A. Okay. How about 69? Order the elements sulfur, chlorine, and fluorine in terms of increasing atomic radius. Okay, ionization energy. How about radius? Well, radius is a little trickier. And in order to get a trend, we have to ignore this section right in here and just look at the representative elements. So what happens as you go from left to right? Radius. You shrink because you're increasing nuclear charge with electrons in the same energy level. So this is decreasing, right? And if we went down, we'd be increasing because we're adding electrons to more shells, outer shells. So it increases this way means decreases this way. So decreasing from lower left to upper right. So if we're in terms of increasing atomic radius, decreasing that way, increasing the other way. So we would increasing atomic radius. So this would be less, this would be then. So it's F, fluorine, chlorine, sulfur. That was the, those are the trends. How many more do I have? Oh, you can't see it, can you? All right, number 73. Of the following elements, which has the lowest first ionization energy? All right, so let's put each one up here and investigate. We got barium, calcium, silicon. Barium, calcium, silicon, phosphorus, chlorine. So the trend, like before, the trend, first ionization energy is increasing. All right, first ionization energy, increasing from lower left to upper right. So let's put these in perspective. Barium is way down here. And then calcium is up here. Silicon is way over here. And phosphorus is right next to it. And chlorine is over here. It looks like it's on the noble gases, but it's not. It's just next to them. So we're looking for the lowest first ionization energy. So it would be on this end. That would be barium. Barium would be the lowest first ionization energy. Now 74 uses the same list. The same list, only asks a different question. Of these elements, which is most likely to form a negative ion with charge 1 minus? The most likely to form a negative would be, now we're not talking about ionization energy, we're talking about electron affinity. And electron affinity becomes, the elements become more attractive to electrons as you move this direction. It takes more energy to drive one electron away, which makes it easier to add an electron. So the one that would be more likely to form a 1 minus is chlorine. It's a halogen. Right? Hello? Hey, were you trying to call me?
Yeah, you called me earlier, didn't you?
Yeah, I've been trying to call you all day long.
Oh. On the house phone or the cell phone?
Both.
Oh, my cell phone shut off
Okay,
and I hadn't turned it on.
okay. Yeah,
Doesn't matter.
well, I didn't get to see you this morning because you were sleeping. And
Okay,
I wanted to caution you not to take any more Neurontin.
okay,
No gabapentin. You had another psychotic break last night.
okay. It's my morning meds yet. I've been sleeping most of the day.
Yeah, probably because you
So
wore yourself out.
yeah. No more medicine like that.
No,
If I take some Tylenol and some Advil.
that'll be fine.
Okay, but I'm not in any pain right now. The only thing that hurts is the bruises on the side of my legs.
Okay,
But the incision itself doesn't hurt.
okay. Is it still draining?
I haven't even got up to pee yet, so I don't know. It probably is.
Yeah, okay. Do
So
I,
I'll do that.
do I need to pick up some more pads on the way home?
I guess so, yeah.
Okay.
If you got some money,
Yeah, I got paid today. What, is that a number 4, the big ones?
I think so, yeah.
Oh, okay.
Okay,
Yeah,
hold on a minute.
okay, sure.
Oh, I haven't even called that phone the hospital yet. Oh, I'm never gonna have this surgery done again, ever. Absolutely never. Oh, that medicine, they gave me something in the hospital that's not reacting well. Um,
Are you talking about the pain medicine?
yeah, the narcotic or whatever it was they gave me.
Well, yeah, your first reaction we thought was the hydrocodone.
Yeah,
And the second time you weren't taking it, so it had to be the Neurontin.
yeah. I never had any trouble with, well, yeah, I did too. The oxycodone, when I had my biopsy,
Yeah,
that made me kind of disoriented, but it didn't make me crazy.
yeah. Well, that's been years ago, so things could have changed.
Yeah, yeah, there's number 4.
Okay. Anything else you need?
And no, I can't think of anything.
Okay,
I got 3 pads left, so.
okay.
And I got a lot of the little ones.
Okay, good.
Okay, are you done with school?
I'm finishing up, I had to break from the lecture to do the lab, and now after the lab's over, I'm coming back and finishing the recording of the lecture.
Oh, okay.
So I can post it for them to finish watching the rest of it.
The test they weren't giving them.
No,
Oh, that was funny.
I figured the weather was April Fool's enough. We thought we were in spring, but no, it's still winter.
Really?
Well, it was cold this morning.
Oh, Yeah, I'm draining a little bit.
Okay,
Not bad, not like it's been. And the pad is pretty.
it'll probably take me another half hour, 45 minutes to finish this thing, and then I'll head home.
Okay, if you think I need some more underwear,
Okay,
get a big size.
okay,
Let me look on this bag here, because these are too small,
okay,
and I'm swollen. Um,
okay.
this, this surgery has wiped me out.
Yeah,
And I don't think only that, but my stamina is not good anyway. Is that the right word?
yeah. Well, the first time around, he just took some of the vulva, right? This time he dug into your lymph nodes and took them. So
That was not good.
no, that was a whole lot more surgical damage than before.
Oh. Get an extra large.
Extra,
What are these? Extra large, what are these? These are large.
okay, extra large.
These are 7 large. 7, either an extra large or an extra large.
Okay,
Because cotton shrinks.
okie doke.
Thank you, sweetie.
Okay.
Oh, freaking all of it.
Okay, I'll see you in a little.
Okay. Okay, love you.
Love you too.
Bye-bye.
Bye. All right, 75. Scroll a little bit there. Which of the following atoms has the largest ionization energy? All right, so I'm glad I left that up there. And I assume that because these are all neutral atoms, that we're talking about the first ionization energy. So we've got oxygen, lithium, neon, beryllium, potassium. Okay, this is a slightly tricky question because remember, if you have valence electrons available, then you rank them according to this arrangement. But we've got neon here. Neon is all core electrons. That means it is definitely going to be the largest first ionization energy of any of those. We don't even have to compare them. All right. Okay, 77. So order, which of these is correctly written in the order of decreasing frequency? So we want to decrease frequency for these order. Okay, rather than write A through E up here and look at them that way, I'm going to put, I'm going to start running down the list and put them in order. All right. So A says visible in the middle. Right, visible. Ultraviolet. So this is going to be let's see. Let's say increasing frequency, but here decreasing frequency would be this way. Decreasing frequency that way. So the higher frequency from visible is the ultraviolet. Right? And then we get to X-rays. So decreasing frequency would be the frequency gets lesser. Higher frequency means higher energy. And this is higher energy. So decreasing frequency, that's correct. No, that's not right. Ultraviolet, visible ultraviolet X-ray. That's increasing okay, that's backwards. All right. We're going this way for that group. It's backwards. All right, so A can't be it. B has radio waves out here. Then visible here. And then ultraviolet. So that's going backwards also. Okay. The C says ultraviolet, visible, and infrared. Ultraviolet, visible, infrared. That's a good one. That goes decreasing frequency. Decreasing frequency is decreasing energy. And we decrease energy from ultraviolet to visible to infrared. All right. So you can assume that D and E are also wrong. All right, I left out microwave here. But we found our answer. Okay, 78. Which has these types of electromagnetic radiation arranged in order of increasing wavelength. Increasing wavelength is decreasing frequency. So it's going to be exactly the same as 77. Right? It's just another way of saying the same thing. So ultraviolet, visible, infrared is increasing wavelength. 79. Right? To 79. Which has these electromagnetic radiation arranged in order of decreasing energy. Same thing, right? Increasing, let's see, order of decreasing frequency, increasing wavelength, decreasing energy, all exactly the same meaning out of three different statements. So this is also C. About 80. Okay. In quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property? All right. This one is energy and size. This is orientation. Right? That's the angular momentum. This is the magnetic. And the magnetic is shape. Let's see, orientation. No. No. This is orientation. Excuse me. This one is shape. There we go. That one's shape. So energy, size, shape, orientation. For instance, if we had p orbitals here, the shape would be like a dumbbell. But these tell you the orientation. So you can have orientation like that on the X and Y axis. You can have a Z axis here also for orientation like that. So these numbers tell you orientation. All right, so the answer to this one is B. The magnetic number is orientation. Who's next? 81. Okay. Angular orbital momentum quantum number. All right, so this is the angular is the shape. That's D. $84. Let's erase a few of them, make some room. $84. Select the correct electronic configuration for copper. And this is an abbreviated form. So that's good for us, right? Copper has 29. Okay. So what we do is we start at copper and we go backwards until we reach the next available noble gas. So copper is in the fourth period. We go backwards. We end up at argon. And argon is 18. Then we work our way forwards again. So we go from argon to the fourth period, and that gives us 4s2. And then we go to the 3ds. 3d, and we work our way over. Copper is in the 3ds. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. That's what we would expect. But this, let's see, we have enough 18, 20, 29. The problem here is that this is not the most stable configuration. When you get to D9, it wants to go to D10. It's more stable. It's a balancing act. So here you have 2 in the S's, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9. To stabilize this one at a lower energy, we take one of these and we put it over here. That makes this 1 and this one 10. So 4s1 3d10 should be the correct one. That's B. That's one of those anomalies. All right, 85. Which of the following equations corresponds correctly represents the process involved in electron affinity? Okay, if we're starting with neutral atom, remember they always have to be gases because we don't want to influence the energy by any phase changes. So this is a gas. Electron affinity means how attractive is that atom to one electron. And we end up with a negatively charged gas atom, right? So C is the best representation of that one. $86. Let's see, we're going to have a change here, so I'm going to go ahead and erase this one. Because the next one is a periodic trend also. 86. So the periodic trend here is we want to arrange atoms in order of decreasing atomic radius. So we decrease from this direction. And we also decrease this direction. Okay. So lower left to upper right is decreasing radius. Now, let's see. Let's take all these elements and put them up here. Lithium, oxygen, nitrogen, fluorine. So lithium is going to go here. Oxygen's going to go like about here. Nitrogen's here. And fluorine is here. Okay. Then lithium, nitrogen, okay, the same ones. Fluorine, nitrogen. Okay, A, B, and C have the same elements. And then D has sodium, strontium, oxygen. Sodium is here. And strontium is down here. And then oxygen and fluorine. And calcium in relationship would be right here. And cesium is way down here. Sulfur is under oxygen. And the last one is selenium. It's under sulfur. Okay. So if we put these in order, right, this is going to be the biggest one. So if we're putting them in decreasing atomic radius, cesium would be the largest one. And then strontium, and then calcium, then sodium, and then lithium. And then we go over here and we get into selenium, let's see. Sulfur and nitrogen might be a toss-up. So that order is kind of iffy. And then oxygen and then fluorine. Okay, let's see which one fits in there somewhere. There's lithium, oxygen, nitrogen, and fluorine. A is not it. Lithium, nitrogen, oxygen, fluorine. That should work. Lithium, nitrogen, oxygen, fluorine. So that would be B. We can look at the others. Like fluorine is not the largest one, so C can't be it. Sodium is smaller than strontium, right? So it can't be it. And calcium and cesium. Calcium is smaller than cesium, so that one can't be it. So we found the right one. It's B. B is the correct answer. All right. Let's see. We have any more? Okay. Let's see. Yeah, I was just checking to see if I need to keep that periodic table up there. I don't think I do. Well, maybe I will. I'm going to leave it up there. Let's go back to where I left off. Let's see. Here we go, 87. Okay. Consider an atom traveling at 1% of the speed of light. The de Broglie wavelength is found to be 1.46 times 10 to the minus third picometers. Which element is this? All right. we're given the wavelength already. Right? So we don't have to worry about calculating it ourselves. So we got to pick it out of those possible ones. How do we determine the identity of an element? We can do it with the Z number, or we can do it with the molar mass. I don't think we can find the Z number out of this information. We're going to have to do molar mass. So molar mass, in order to do molar mass, we need mass per unit moles. Okay. All right, what do we know? We know its velocity. Its velocity is equal to 1%, which is 0.01 times 2.9979 times 10 to the 8th meters per second. So that's equal to, let's see, 1, 2. So it's 2.9979 times 10 to the 6th meters per second. That's the velocity of our atom. And at that velocity, its wavelength is 1.46 times 10 to the minus 3 picometers. Okay. Now, we need to have all these values in SI units. So what does that mean? Pico is 10 to the minus 12th. So this will be 10 to the minus 12, 10 to the minus 15 equals 1.46 times 10 to the minus 15 meters. That's the wavelength. Okay. Now, what else do we know? Well, we know, and we're looking for formulas that have mass in them. So one of the first ones I think of is Einstein's equation. Right? But for our purposes, we should be able to equate that to mass times velocity squared. Okay. We also know that energy equals is the Planck's equation. Energy equals Planck's constant times frequency, or Planck's constant times the speed of light over wavelength. But we're talking about an equivalent wavelength for a particle. So we're not talking about the speed of light anymore, because we're not talking about light. We're talking about matter. So we're going to substitute in here velocity and wavelength. Okay. So now we can set these two equal to each other. Right? We can say E equals E, which is mv squared equals Planck's constant times velocity divided by wavelength. Okay. So what does this actually mean? It means this relationship is true for one atom. So if we combine terms and we're looking for mass per atom, then we want to put the v squared over here, right? So mass equals h v over v squared lambda. So we cancel this one, and it leaves us one down there. So if we want to do our calculations, we say the mass of that one atom is Planck's constant, 626 times 10 to the minus 34 joules seconds. And we probably want to use the alternate measurements for Planck's constant. And let's see, kilogram meter squared per second. So rather than that, we're going to use kilogram meters per second. I think that's right. Yeah, that's right. And this is divided by the velocity, which is, let's see, velocity. Here it is. Velocity 2.9979 times 10 to the minus 10 to the sixth meters per second. And that's times wavelength, which is 1.46 right. Excuse me. 1.46 times 10 to the minus 15 meters. Okay. So now, this is in the denominator, that's in the numerator. Meters cancel. Actually, I should write this out. Mass. So we won't get it confused with meters. Well, actually, we got meters here and meters there. Why don't we leave that one alone and cancel this one instead? No, sorry, I can't do that. This is in the denominator, right? This is in the numerator. That has to cancel. And this continues to be in the numerator. Okay, what else can we cancel? Well, this is in the denominator here, and it's in the denominator there, so the seconds cancel also. Okay. Calculator. All right. 6.626 exponent negative 34 divided by 2.9979 exponent 6 and divided by 1.46 exponent 15 negative. So I get, let me see if that looks right. Yep. So this is going to be in kilograms. This is, so the mass per atom equals 1.5138 times 10 to the minus 25 kilograms per atom. Okay. We want to convert that to grams per atom. Actually, we can do the whole thing. So let me make some room over here. And we're going to do some unit conversions. Let's change kilograms to grams first. That's 1,000. Then atoms, we want per mole. Grams per mole is molar mass. So we got 6.022 times 10 to the 23rd atoms per mole. Now the atoms cancel. So this is grams per mole. I get 91.2 grams per mole. That should be our molar mass. So let's look up 91.2 is zirconium. Okay, that would be B. All right. That was 87. Okay, who's next? 88. I think I need a new marker. In an investigation of the electronic absorption spectrum of a particular element, it's found that a photon having wavelength 500 nanometers provides just enough energy to promote an electron from the second quantum level to the third. From this information, we can deduce. So if that's just enough energy to go from 2 to 3, right? Just enough energy. We can say the energy of the n equals 2 level. Can we deduce that? No. All we can deduce is the difference in energies between the two. So A and B are both false. The sum of the energies? No. The difference of the energies between N2 and N3. That's what this wavelength allows us to deduce. That quantum of energy required to promote the electron. All right, so D is the answer. All right. '89. '89 is based on that chart. In the hydrogen spectrum, what's the wavelength of light associated with N equals 3 to N equals 1 electron transition? So if it goes from 3 to 1, so N3 to N1, the final minus the initial, right, would be N1 minus N3. So minus 2.178 minus 2.178 times 10 to the minus 18 minus 3. 0.2420 minus 0.2420 times 10 to the minus 18 joules. Yes. Okay, so this is the energy transition, the change in energy. Get my calculator. Okay, we know it's going to be times 10 to the 18 because both powers are the same, 10 to the minus 18. We just need to calculate this part. 2.178, change the sign, and then 0.2420. So I get minus 1.936 times 10 to the minus 18 joules. All right, when we do the calculation to find out the wavelength, we're using Planck's equation. And we're going to use, speed of light over lambda. So there's the energy. And the energy transition if it's going from 3 to 1, it's going to give up a certain amount of energy. How much is it giving up? Well, in absolute terms, it's giving up 1.936 times 10 to the minus 18 joules. So we don't need the sign. We just need 6.626 times 10 to the minus 34 joule seconds times 2.9979 times 10 to the 8th meters per second. And then lambda in terms, lambda is our unknown. And the energy is 1.936 times 10 to the minus 18th joules. So we just need to solve for this value. If we bring that value over here, put that value over there, right? Put that one over here and take this one and put it over here. Then we can do that calculation. Oops. 34. 6.626 exponent negative 34 and 2.9979 exponent 8 and divide by 1.936 exponent negative 18. Divide. So I get a wavelength equals 1.026 times 10 to the minus 7 meters. Okay. Our answer is given in what? Nanometers, centimeters. Well, 1.03 times 10 to the minus 7th is there, right there, E. So we don't have to make the other conversions. Right? This is E. Selection E. If E were not the answer, the best way to approach the problem is to convert. Don't convert this one to centimeters and nanometers. Just convert the nanometers and centimeters to meters. It'll be easier that way. And then you can compare those numbers to this one. All right, number 90 is using that same chart. Right? What's the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from N5 to N1? Okay, so if it's going from N5 to N1, what we want is a change in energy equal to what? 1 minus 5. So 1 is still minus 2.178. 2.178. And I'm going to do it this way. Minus 5 is 0.08712. And this is all times 10 to the minus 18 joules. Okay. So 2.178, oops, 8, change the sign, and then 0.08712 add, and I get minus 2.099 times 10 to the minus 18. Now we can plug that into our formula. Let's do it this way this time. If we have energy here, and we have Planck's constant and C over wavelength, the question is, what's the wavelength, right? What's the wavelength? So let's go ahead and solve it for wavelength. Put the wavelength over here. That's Planck's constant times speed of light divided by energy, and that's it. So 6.626 times 10 to the minus 34 joule seconds times the speed of light meter per second divided by the energy, and we only need the absolute value. 2.099 times 10 to the minus 18 joules. The joules cancel, seconds cancel, leave us with meters. I get 9.464 times 10 to the minus 8 meters. 9.46. Close enough. 9.50 would be B. All right, that was 90. Let's see who's next. 91. Which of the following is a reasonable criticism of Bohr's model of the atom? Okay, remember Bohr's model. We had a nucleus and we had orbitals, this, and then they get closer and closer together, like this, right? So this is 1, 2, 3, 4, and we could keep going. Okay. What does A say? It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Which of the following is a reasonable criticism? Well, that is a criticism, yes. Why doesn't the electron, if it's an orbit like this, why doesn't its orbit decay and it fall into the nucleus just like any planet would, or any satellite would, traveling around the Earth? But there's probably a better answer. A is reasonable. Yeah. A, possibly. B, it does not adequately predict the line spectrum of hydrogen. That's false. Right. B is not a reasonable criticism because it does predict the line spectrum. It doesn't adequately predict the ionization energy of the valence electron for elements other than hydrogen. That is definitely a criticism. If the atom is not hydrogen or hydrogen-like, in other words, only one electron, then the Bohr model doesn't work. D and E. D says it does not adequately predict the ionization energy of the first energy level electrons for one electron species for elements other than hydrogen. It makes no attempt, right? So based upon that, it makes no attempt to explain. That would also disqualify A. So D is disqualified. Just because it doesn't explain it doesn't mean it's a reasonable criticism because it doesn't attempt to explain it, right? You can't fault somebody for not trying to explain something, right? You can't prove it, disprove a negative. E, it shows the electrons to exist outside of the nucleus. That's not a reasonable criticism because that one's already been proven, right? By Ernest Rutherford. He proved the nuclear model already. So Bohr doesn't have to even deal with that one. That's a presupposition. That's a postulate that's just built into the model. It has to be that way. 93. Okay, we can get 93 on there. Okay, which of the following statements are true? Okay. 1, 2, 3, 4, and 5, I think. Yeah. So 1, Is one true? An excited atom can return to its ground state by absorbing electromagnetic radiation. False. It must emit radiation in order to return to its ground state because it's moving to a lower energy. Energy must be conserved, so it has to give up that energy. Right? So this one is false. Roman numeral 2, the energy of an atom is increased when electromagnetic radiation is emitted from it. False. It becomes more stable. It's lower energy when it emits radiation. That one's bad too. Roman numeral 3, the energy of electromagnetic radiation increases as its frequency increases. Yes. Energy increases as frequency increases. That's true. 4, an electron in the N4 state in the hydrogen atom can go to the N2 state by emitting electromagnetic radiation at the appropriate frequency. Yes, indeed. It goes from a higher energy level to a lower energy level and emits radiation. Sure can. Roman numeral 5, the frequency of wavelength of electromagnetic radiation, the frequency and wavelength of electromagnetic radiation are inversely proportional to each other. Yes. C equals wavelength times frequency. So 3, 4, and 5 are correct. 94. Consider the following representation of a 2p orbital, right? Looks like a dumbbell, sort of. Which of the following statements best describes the movement of electrons in a p orbital? Okay. Well, let's take them one at a time. A, B, C, D, and E. A says the electrons move along the outer surface of the p orbital similar to a figure 8. We're not saying anything about the movement actually, right? Because we're concerned with the energy, and the position of the electron would imply that we know how it's moving. Right? So that one's false. It doesn't move along the surface. The electrons move within the 2 lobes of the p orbital, but never beyond outside surface of the orbital. No, this is a probability model. In other words, this is the most probable location for the most probable location with that as the nucleus. Now, the electrons could be out here, but the probability drops way off. It's very improbable to find electrons out here. But still, that makes B false. How about C? The electrons are concentrated at the center, the node of the 2 lobes. No. That node means we are giving the probability of finding an electron there a value of 0. That's what a node is. So C is also false. And D, the electrons are only moving in 1 lobe at any given time. Like I said before, this is a probability distribution. The electrons could be anywhere in that space. And E, the electron movement cannot be exactly determined. Bingo. Heisenberg's uncertainty principle says, if we want to know the velocity, we want to know the energy of our electrons, we can't know where they are exactly. And since we prefer energy information versus position information, then statement E is the best compromise. 95. How many electrons can be contained in all of the orbitals within n equals 4? All right. So here we've got n equals 4 right here. So how many L's can there be? Well, there can be 0, 1, 2, and 3. Okay? Within each one of these, this one can have a 0. This one can have -1, 0, and +1. Next one have -2, -1, 0, +1, +2. This one can have -3, -2, -1, 0, +1, +2, +3. Okay, so the number of orbitals that are possible would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 orbitals. Oops. Oh, electrons, excuse me. Times 2 electrons each equals 32. Okay. So I wonder if there's a relationship here. If we take n equals 4, if we square 4, we get 16. What if we had n equals 3? If we had n equals 3, then we would cut out we cut out this one. And that would be 1, 2, 3. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 squared. So that's equal to 16. That's equal to 9. What if we only had 2? Right? If we had 2, 2 squared would be equal to 4. Right? So that would be 0 and 1 possible. And then 0, 1, 2, 3, 4. That looks like a reasonable approach, right? If you want to know the total number of orbitals from n equals 4, square it. And then times 2 would be the number of electrons. Okay, 96 coming up. The small but important energy difference between 3s, 3p, and 3d orbitals are due mainly to the small difference between those, since they're all principal quantum number 3, so they're very similar in energy, but slightly different. Which one has the lowest energy? The s orbital, then the p, then the d. What is it based upon? It's based upon the penetration effect. 3s orbitals penetrate closer to the nucleus than 3p's, and 3p's closer to the nucleus than 3d's. So the answer to that one is D, the penetration effect. 97. Which of the following was not an elemental property usually predicted by Mendeleev for as yet unknown elements? Okay. Mendeleev knew nothing about electrons. Electronic configurations? No. So A is the most reasonable answer. He did know atomic mass. He did know densities. He knew boiling points. He knew oxide formulas, right? We didn't talk about that one, but most of the metals and many of the nonmetals can be found as oxides. And that is important information. If you don't have higher energy ones, would be the first to go. If we just took those two, then you have an E2+. Then if we took these two, you would have an E4+. Okay, so let's make a fluoride out of that one. If you have a fluoride here with a 1- charge and a fluoride here with a 1- charge, this would be 2 and this would be 4. So EF2 is a possibility. It's not there. EF4 is B. That's your best answer. Now this element happens to be, let's see, 5p2 is 10. And as it turns out, measurements of its valence charges is it can either be a 2+, or a 4 plus. And that's from practical measurements. Okay, who's next? Um, 104. Which of the following atoms would have the largest second ionization energy? Okay. A, B, C, D, and E. And we're going from magnesium, chlorine, sulfur, calcium, and sodium. Okay. So magnesium's valence shell electrons would simply be 3s2. Right? Chlorines would be 3s2, 3p 5. Sulfurs would be 3s2, 3p 4. Calcium would be 4s2. And sodium would be 3s1. Okay. So we know the trends for first ionization energy, right? Lower left to upper right. But when you talk about second ionization energy, you have to take into account both the nuclear charge and whether or not the second electron is coming from a valence shell or a core. So second ionization energy for magnesium, they're both valences. So it's going to be low. I don't think that's going to be 1. Calcium also has 2 coming from the S, right? Its first and second ionization energies are going to be incremental, but not massively different like you would expect from an extraction of a core electron. Sulfur, right? We're still taking them from this valence shell, right? So it wouldn't work. With chlorine also. With sodium, though, where is sodium going to come from? 3s1, it'd be 2p6. Once you take that one out, you're going to try to extract an electron from a core. So this is your best answer. Sodium would have the largest second ionization energy, simply because the electron's coming from the core. (107). Which of the following concerning second ionization energies is true? Probably follows from the previous one. We're comparing, it looks like aluminum and magnesium, second ionization energies. Okay, so let's do this. So what do we got going for aluminum? Aluminum has 3s. Well, let's just draw it out. 1s2, 2s2, 2p6, 3s2, and 3p1. And magnesium is 1s2, 2s2, 2p6, and 3s2. Okay. Then we look at our choices concerning the second ionization energy. So the first ionization energy would take this p electron away, right? If we did that, that would make this one a +1. The second ionization would take an electron still from a valence shell. So it's gonna take some energy, but not a whole lot. Magnesium, first ionization energy would take it from S, and that would give us a +1. And then the second ionization energy is taken from S. But look at it this way. Okay. It's going to be easier to remove that electron for its second ionization energy because it's repelled by the other electron. Whereas this one doesn't have a repulsion to deal with. So it's going to take more energy for magnesium. All right, let's see what it says. A says that aluminum is higher than that of magnesium. No. Oh, wait a minute. Okay, why would aluminum, if aluminum was higher than magnesium because the electrons are taken from the same energy level, but the aluminum atom has one more proton. Okay, I didn't consider that. How many protons? Aluminum has 13. Magnesium has 12. Okay, when you throw protons in there, that's true. Because the first ionization energy is higher for aluminum than it is for magnesium. And you would expect the second ionization energy to also be higher. So there are multiple factors involved here. B seems to be the best answer unless C, D, or E has something extra to say. Aluminum is lower than magnesium? No. Aluminum is lower for D? No. Second ionization energies are equal. Highly unlikely that they would be exactly equal. So I think B would be the best answer simply because the difference in protons. And if we follow the trend from left to right, and not on radius, but increasing ionization energy, it's because of the increased nuclear charge. So that would explain it simply because these electrons are coming from the same shell, the same subshell. All right, 108. Consider a planet where the temperature is so high that the ground state of an electron in hydrogen atom is N equals 4. What is the ratio of ionization energy for hydrogen on this planet compared to that on Earth? Okay. So on Earth, you've got an atom. Oh, we got hydrogen. So this hydrogen is going to be electron in the number 1 shell. On our exoplanet, right? The hydrogen now is going to be 1, 2, 3, 4. That's where the ground state of the electron's located. So what's the difference with the ratio of the ionization energy? Well, this is going to take less energy to be removed. The ratio of ionization energy for the hydrogen on this planet compared to that of Earth. So it's going to take less energy here than it does there. That means, let's say this is exoplanet. Let's say HX versus H. So the ratio of the ionization energy for this one divided by this one is going to be some number that's less than 1 because it's going to take less energy here than it does there. Right? If this were in position 1, then they'd be a 1-to-1 ratio, but they're not. All right. So what's the difference in the ionization energies? Well, let's see. Can we do this without actually using numbers? Well, look at it this way. What does the ionization energy mean? Ionization energy, ionization energy. It means the amount of energy to go from N4 to infinity versus N1 to infinity. That's what we're saying. So when we do the subtraction, if we go from N4 to infinity, we're going to the same place, but we're starting from a different location. All right. So what's the formula? We could do it with the absolute calculation, but I think there ought to be an easier way to deal with this one. Let's look at the formula that's used. Let's see. Let me just scroll down. Come back to 108. Okay, keep going. All right. Where is it? Here it is. So the energy for any one electron is that constant minus 2.178 times 10 to the minus 18th times z squared over n squared. Okay. So the difference would be the infinity minus, let's see, yeah, infinity minus your position here, and the infinity minus the position there. So if we say, let me erase this. What's the energy required here? Well, the change in energy required for the exoplanet is minus, well, it's a final state, E final, which is B infinity minus E4. And the one for Earth, let's put an E down here for Earth. Yeah, E. There you go. Equals the final minus E1. Okay. So the ionization energy is going to be this change right here. So if we ratio them like this, then what is this expression going to be? Right. Well, the energy of the electron at infinity is 0. That's by definition. So we really only have to ratio these two, right? E4 over E1. So what's that expression? Well, we have that constant, right? Minus 2.178 times 10 to the minus 18. But it's in both of them, 178 times 10 to the minus 18. So it drops out. And each one of these is multiplied by just a second. Yeah, okay. I'd pause for a second. So this is going to be z squared. This is going to be z squared. This is going to be n squared. This is going to be n squared. But this is for the fourth level, and this is for the first level. Right? well, I shouldn't put that in there because N is equal to the principal quantum number. Z is equal to 1, right? So this is going to be 1. And this is going to be 1, 1, 1. This one is going to be 4. And this one's going to be 1. Okay? So these cancel. And you get 1 over 16 divided by 1 over 1. So the ratio, this divided by 1, the ratio is 1 to 16. Let's go back to 108. 108. That was a difficult description, but the ratio of the exoplanet to the Earth energy required is 1 to 16. Take it a 16th of the energy to ionize that electron on the exoplanet as it does on Earth. That's what we're saying. Okay, I think we're done, actually. I didn't pass any other yellows. Yep, we're done. All right. And just a reminder, remember on the 10th of April, don't come to class, don't Zoom in because I'm not going to be here, right? It's a buffer day. So you're not going to miss anything. Just keep up with your homework, keep working on your lab reports, and prepare for the exam. I think the exam, we'll have a review. I think it's a review. When we come back after the 10th, we'll do the review for the next exam.